Runout is the inaccuracy of rotating mechanical systems, specifically that the tool or shaft does not rotate exactly in line with the main axis. Runout in a drill press can result in a larger hole being drilled than the actual size of bit being used. In this video, we're going to be discussing runout, how to detect it, how to correct it, and some of the various causes of runout in a drill press. Hello everyone, I'm Jeff and welcome to my shop. We got a lot to cover, so let's get to it. I have chucked a milling bit into my metal lathe and I have a dial indicator set up and it's zeroed out. And if I rotate this chuck by hand, we're going to detect less than 1/100,000th of an inch of runout, and there it is. And that's because there's probably an imperfection on the shaft of that bit, like a scratch or a gouge. But otherwise, there's no noticeable runout in that bit. And we're not getting a lower indication on the opposite side of where we're getting that 1/100,000th of an inch bump. So we can assume that this bit is relatively true, and we can also assume that my metal lathe has basically no runout in it. When we look at a drill press, there are a variety of factors that can affect runout. Of course, the ultimate point of where the bit is chucked into that chuck is where you want to check your runout initially. However, before we get to that part, let's take a look at the inside of a drill press. This is a Classic Craftsman 100 or a 150. They're basically the same on the inside. And even the Emerson later models are basically the same on the inside. This cutout is brought to us by Frank Lee, a good friend of mine. So quickly, I'm just going to point out all of the points of contact that could affect runout in this drill press. At the very bottom, you have your taper on the end of your spindle, and that's where the chuck connects to the spindle. Above that and inside the quill, you have a ball bearing. And above that, you have the bottom bore for the head casting that the quill rides in. Then you have the pinion. Then you have another bore for the quill to ride in, and there could even be a third bore. And then at the top of the quill, you're going to have another ball bearing. And then coming out of the top of the quill, we have the spindle where it engages into the spindle pulley assembly on its splines. And then the spindle pulley assembly has two ball bearings, and both of those ball bearings rest in bores in the top of the head casting. So every one of these points of contact affect the end result of runout. But the easiest ones to correct are your ball bearings, and they're also the ones that have the most play in them because they're moving components. So let's quickly talk about ball bearings. All of the 15.5-inch Classic Craftsman Drill Presses, whether they're made by King Seeley or Emerson, except for the commercial models, utilize the same quill ball bearings. And for that, they need a 6202 special 5/8 bore ball bearing. Right here, we have three 6202s from NSK, and each one of these ball bearings is different. The top one is a 6202 standard ball bearing. So its inside bore measurement is 15 millimeters, whereas the bottom two are both 5/8 bore, special bore ball bearings. So they actually measure out at 15.875. And that difference is huge, and you have to use the correct ball bearing. You have to have a 5/8 ball bearing in that quill for it to work properly. So the bottom two ball bearings are basically the same ball bearing. The main difference between them is the bottom one is shielded and it has metal shields on it, you can see, whereas the one in the middle has a seal on it. And that seal can be made out of rubber as well as a couple of other materials. Because ball bearings are a generalized transfer device, they transfer energy from one part of something to another. They are designed to fit a variety of situations where you're going to use a ball bearing. So one of those situations may call for a shielded ball bearing, and one of those situations may call for a sealed ball bearing. Regardless, on a drill press, we're pretty much open to whichever you want to utilize, because we're not moving at such high rates of speed and we're not moving under such great loads that friction is truly going to become a problem unless you're running that drill press 24/7, 365. So all of the King Seeley drill presses and most of the early and middle year series of Emerson drill presses came with shielded ball bearings, but you can certainly use a sealed ball bearing in any of these drill presses. The last thing I want to point out in this image is on the very bottom ball bearing, you'll see the model number is NSK 6202-10ZZC3. ZZ means that it's got metal shields on both sides. The 10 indicates that it's a 5/8 bore. And the C3 is the bearing clearance. So quickly, this is a graphic just showing you your different types of closures for those ball bearings. You have your shielded type and then you have your seal type. And if you look on this chart, you can see the speed capacity and then the allowable temperature ranges. And the more sealed the ball bearing is, the more susceptible to temperature it's going to be. This image shows the inside of a ball bearing. And you have the balls, you have the cage, you have the inner ring, which is also referred to as the inner race, and then the outer ring, which is the outer race. And then you would have your shields or your seals on the outside. So bearing clearance is basically how much play the ball bearing has itself, inside, internally. And this is before the bearing is put under load. If the bearing is installed properly and it's under the proper load, then there should be basically no clearance once the ball bearing is operating, no detectable clearance. But it's important for us to understand that you've got that radial internal clearance and that axial internal clearance that can translate into runout. So I'm trying not to get too technical here, but basically ball bearings come in a variety of clearances from C1 to C5. And you might see a CN, which is just normal clearance. C1 is smaller than C2. C2 is smaller than normal. Normal is normal. 3 is greater than normal. 4 is greater than 3. And 5 is greater than 4. And all of that is based on equations. So it's never going to be the same unless you're dealing with the same size ball bearings. So this is just a chart showing you the minimum and maximum amount of radial internal clearance based on the bore diameter, which is on the left. And you've got your C2, your CN, C3, C4, C5. When we're talking about drill presses, really anything from C3 down, so C1, C2, or C3 is fine. You're probably not even going to be able to find C1 ball bearings without paying a lot of money. So most of your ball bearings out there for drill presses are probably going to be in that C3 category. So assuming you have a C3 ball bearing in your drill press, then the way you're supposed to minimize that clearance and translating into runout is you are supposed to preload those ball bearings. But for most of us out there, we're not going to have the wherewithal or the knowledge of how to preload those ball bearings, and we just end up sliding them on the shaft and then sticking them in the drill press. And on a C3 ball bearing, it is not going to make that much of a difference that you need to worry about it as far as run out. So I've seen a lot of videos out there on YouTube about how to measure run out on a drill press, and some of them are accurate and a lot of them are not. So let's get into this. Basically, you need to remove the belt from your spindle pulley assembly. And on my drill press, I've got an MSA or slow speed adapter, a center pulley, if you will, in the center of my column. So I have to loosen it, and then I have to loosen the motor lock screws and relieve the pressure on the very back belt, and then relieve the pressure on the front belt. Once we have the belt off of the spindle pulley assembly, we need to set up an indicator, and this is just a dial indicator on a magnetic base, and utilize something that we know is fairly true, being round. And so we're going to use that same mill bit that I had in the metal lathe, and we've put it into our chuck. And we've tightened it down on all 3 tightened down points in the chuck itself. So we've got it as centered as we can get it. So real quickly, I've seen a lot of videos out on YouTube where they're trying to check the run out on the chuck body or on the chuck sleeve or even on that safety collar, and none of those matter. The outside of those items have 0 effect on run out. So what you need to be checking is something chucked inside the chuck connecting to the jaws. And I should also mention that the quill is completely retracted inside the head casting to give it its most stable platform to check the run out. And to avoid cosine, you want that dial indicator as perpendicular to the shaft as possible. Less than 10 degrees is how you're going to avoid cosine. Sorry, I'm adjusting the camera here. But we're now going to just rotate the spindle pulley by hand on top of the drill press and then look at that detectable amount of run out that's in this drill press. There's 10, 15, 20 thousandths, 23, 20, oh, 4, 30, 30, 34, 34 thousandths in one direction. And 17 in the other. And that gives us a horrible 51 thousandths of an inch of run out. So before we start panicking, let's pull the mill bit out, reseat it, and readjust the dial indicator and check it again. And there's 10, 15, 20. It's not looking good. 23 in one direction. And just one. So 24 thousandths of an inch. That's a little better. And we definitely have the dial indicator perpendicular now to the bit, so there's no cosine error there. That's a little better, but that's still horrible. So we are going to take off the chuck and check the taper for run out. And given the age of the chuck that's on this drill press, it's very possible that that is exactly what's causing the run out to be as severe as it is. And we talked about all those contact points inside the drill press, but we didn't talk about the contact points inside the chuck. And there are several of them there. The most obvious being the face of the jaws. So we can remove that chuck and then check the taper. So here we are basically with the same setup, except we're checking the taper now. And we're zeroed out. And we're going to then just rotate the spindle pulley assembly by hand. We've got 2, 3, 4. So 400 thousandths run out on the taper of the spindle, which isn't too bad, but it can still be better. So I just recently rebuilt this drill press, so I know the bearings in it are brand new. They're good to go. So obviously the chuck needs to be replaced, but in addition to the chuck, we can correct that 400 thousandths of an inch on the spindle. And this is how I correct it. I chuck the spindle inside my metal lathe, and we already know that the lathe is true. We checked that earlier. So we can put dial indicator on the spindle, and it actually does matter where on the taper we put it. If we put it as close to the same spot that we had it in the drill press, we should get back relatively the same reading. But the taper itself may not be 100% true. And if you've had a drill press that you rebuilt and there was compound on that taper or any deformity on the taper, you could get back a bad reading. But basically, we're just going to rotate the chuck by hand and see what kind of run out we're getting. There's 2 and a half, so 2.5 is what we're getting right now on the taper. And that's probably correct for where on the taper we are now. So in my experience with the Craftsman drill presses, all of your run out is going to be from the bottom bearing in the quill down through the taper, somewhere along that line there. And that's because of some lateral force being applied to the drill press spindle or the chuck. And so that's where I have it chucked inside the lathe, is where that bearing meets. And so what I'm going to do is I'm going to roll it and find the high spots and the low spots, and I'm going to mark those with a Sharpie. And then once I know where the high spot is, the low spot should be directly opposite the high spot. And if it is, then this is an easy fix. And by easy fix, I mean dead blow hammer, rubber mallet, smacking it on the high spot, and then rechecking it. Now when you do this, the dial indicator is going to move, obviously. But wherever it's sitting, we want to then just check and see. So we've got 1, so 1/100 thousandths of an inch, and we can still correct that. And I'll just continue this process until I get basically no run out. And then we can reassemble everything and install a new chuck and see what we get at that point. So one more time, this is going to be on my Emerson Gen 4. I've got a relatively true rod chucked inside the chuck. I've already disconnected the belt, and we're going to just spin the spindle pulley assembly by hand. And we're at a slight angle here from the dial indicator, but it's actually set on 0. And as we rotate that spindle pulley assembly, it looks like 4, but we're really only getting 3. So we're 3/100,000ths of an inch out, which is acceptable for what I use it for. Well, I hope all this has made some sort of sense and that you now have an understanding of how runout occurs in a drill press and how to correct it if it's in the spindle, the bearings, or the chuck. If you found this helpful, please like and subscribe. And I appreciate all the support. And as always, I will see you next time.